Hello, everyone. Come on in. Anybody have any questions before we get started? Looks like we only got 6 of you so far. All right. Well, last time we talked a little bit about the twin paradox and the ladder and the barn paradox, and we worked that out. And the main purpose of those paradoxes was to show once that, of course, paradoxes can't exist in science, but also to show that the idea of time dilation, which we already realized was a relativistic thing. So we already got time dilation in relativity. But what we didn't get was the idea that a difference in times, for instance, the time difference between when the front of the ladder lined up with the back edge of the barn and the back of the ladder lined up with the front edge of the barn and the dad closed the door, that time interval in the dad's frame was 0. So that's the delta t equals 0. And if you look at, for instance, the time dilation equation, if one of those delta t's is 0, either the delta t or the delta 0 is 0, the other one's automatically got to be 0. But by looking at the ladder and the barn paradox, we see that it's in fact not necessarily a delta t always equal to 0. In fact, what we found is delta t equals 0 is not necessarily delta t equals 0 in another frame. So that was one thing. Of course, we also showed that if we can verify whichever one is actually moving by some method, then we can go back and say, no, you can't claim that you were moving versus I wasn't moving, and say, of course, that my brother is the younger of the two twins after the experiment, as opposed to me being the younger of the two twins. Sometimes that stuff just don't work out for my brother Brian. Anyways, so we did that. We did time dilation, length contraction equations. What I want to do now is go ahead and show you Galilean relativity versus Einstein relativity, and specifically talk about coordinate transformations. And once I have those equations, I'll also mention to you that you can use those equations to calculate time dilation and length contraction as well. That's a good thing for you to do. It's a good thing for you to practice. And of course, you should probably keep those Lorentz contractions memorized, but I did get a chance to put up the actual PDF of all the equations for all the chapters from our textbook. So that's now in the important documents page on Canvas. So again, one of my students had found one online somewhere in PDF form. He sent it to me. I posted it in the important documents and pages, our important documents and links section of Canvas. So does anyone have any questions before we get started? All right, so I'm going to go ahead and turn on my document cam. And in so doing, I am going to write out basically 2 coordinate systems. And this is a very special circumstance that we're choosing to make it. And it's only, the results we get are only true for that. There's a more complicated aspect that has to be done if it's not this way. So what we're going to do is imagine an X and Y coordinate system. So what you have is an x-axis, which we call positive pointing to the right, and a y-axis, which we call positive pointing up. And we'll imagine another axis, x prime and y prime, that is identical to this one at x equals 0. So x prime, y prime system. Evidently, I'm going to spell system without a T in it. System. It's a system. So system identical at t equals t prime equals 0. In other words, when the time interval is 0, when the actual time is 0 time, they lie right on top of each other. That means the y-axis is going to be parallel to the y-axis. The x-axis is going to be parallel to the y-axis. But if we take some time later, what's going to happen is we'll have an axis x prime over here and an axis y prime over here. Notice they're still saying parallel. That's the key point. The equations that I'm going to give you are only for this case. And if you were going into relativity, or you had a more rigorous, brutal instructor, he would have actually made you derive these expressions for the axis being oriented in any possible way. So we could have the x-axis pointing up here, the y-axis pointing out of the page, and the z-axis being right-handed, maybe pointing down or something like that. And you could work out another conversion factor for that. But we're just going to stick to this one. So what we're imagining is this frame is actually moving with a velocity v. And if you take this point in space right here, this corresponds to the point x prime, y prime. But after time t, since at time t the origins were the same, we know that this distance from here to here is actually vt. So that's how much time has actually passed by. Now it's kind of weird, but that basically gives you, in Galilean relativity, that gives you x is equal to x prime plus vt. That gives you y is equal to y prime, z is equal to z prime. And then, of course, duh, t is equal to t prime. There's no relativity in time, right? So yeah, we're not changing anything. Well, when you go to make the equivalent of this for relativity, it turns out that, and there's ways you can come up with this on your own. I'll explain some in a second. But you will get not x equals x prime plus vt. You'll get x equals, there's that famous gamma again, x prime plus vt prime. Notice everything on the right-hand side is going to be primed, and all the coordinates on the left are going to be unprimed. Y is equal to y prime, z is equal to z prime, and that's mainly because y and z are perpendicular to the velocity, so they're not going to have any relativistic changes. But here's the really weird one. T is again not going to be equal to t prime, but it's again going to have a factor of gamma on it, and then it'll be t prime, but then it'll be vx prime over c squared. And it turns out that that is the actual Lorentz transformation. Now, actually, Lorentz worked all this out when he got his bad results for his detection of the ether. So they had worked out a way in which you could detect the ether as the Earth flew through it. And they basically set light in two different directions, perpendicular to one another. And of course, if you're moving through an ether, then you'd expect us to be moving with one velocity relative to the ether in one dimension and a different velocity in another dimension. And then after the experiment, you twist the system 90 degrees and you should get a difference. And what they got was no difference. So what he did was worked out a way in which the ether was being compressed by some weird forces of ether nature, and he got these equations which ultimately allow you to come up with the time dilation and length contraction. But he was trying to save the ether. It wasn't an understanding of a deeper understanding of physics. He just was really good at mathematics and managed to get the formula right because he's a smart man. Einstein, on the other hand, just took his two little postulate, the laws of physics are the same for all inertial observers, and the speed of light is a constant independent of motion of the source and the observer, and came up with this exact same expression. Now, since the speed of the light is a constant, you could actually, in principle, consider light leaving a particular point in xy space and in x prime y prime space at t equals 0, and then say, okay, well, where will the front of that beam of light be, a particular point on that front, be sometime later in the xy frame as well as in the x prime y prime frame. And then because those speeds are the same, you can set the c equal to each other and derive these same expressions. So there's neat ways to go about doing that. There's other ways too. You can assume it's sort of a linear approximation to the other frame and then just work out algebraically what it would be. So there's a lot of ways you can come up with this. But now that you have it, you can see, wait a second, if I considered x prime, one of the x prime locations to be, say, the origin, x prime equals 0, and another x prime to be at a position L0, where L0 is the proper length of a rod, then I can calculate what x0 minus xL0 is compared to x0 prime minus x0 L0 prime. Of course, that would be done at the same point in time, and lo and behold, you'll get the length contraction formula. And you can do something similar to that to get the time dilation formula. So just to rehash that, of course, the time dilation, delta t, is equal to gamma delta t 0. And just in case anyone forgets, gamma is defined to be 1 over the square root of 1 minus beta squared, and beta is defined to be v over c, okay? And then the length contraction is L is equal to L0 over gamma. So you can get that from those. Now that we have all those, your book and your homework will actually ask you problems like they'll not only ask you to convert a x prime, y prime, z prime, t prime to a x, y, z, t, but they'll also give you some weird problems like where they give you an x prime, but they give you a regular t instead of a t prime, or they'll give you a t prime, but instead of an x prime, they'll give you an x, and you'll have to work it backwards. So these equations are what's used for that. So we now have quite a few equations at our disposal for relativity, and I'm going to give you a few more in a second. By the way, if you wanted to solve the other way around, you just say x prime is equal to gamma. Now you're going to replace the v with a negative v, and you'll get x minus vt. Notice everything on the right has no primes. So y prime is equal to y, z prime is equal to z, and of course t prime is equal to gamma t minus vx over c squared. Again, notice everything on the right is non-primed. So that's the Lorentz transformation to go from this frame back to that one. So some other things we need to know, and I'm not necessarily going to derive them for you, but your book talks about how they're derived. I derive on my YouTube channel, I derive the addition of velocities formula, which I'll give you in a second. And I've actually already gave that to you back in like chapter 2, I think. But either way, here's some other things. It turns out that momentum, P, which we recognize as mv, in relativity, it actually becomes P is equal to gamma times mv. And from Newton's second law, summation of forces is equal to dp dt. It turns out that is the P that we've got to use when we're using Newton's second law. It's gamma mv. Okay, so that's some new stuff that we're not familiar with. Also, it turns out that there's this famous equation E equals mc squared, which is actually more helpful than you might know. In fact, it's actually true at all times. Okay, what do I mean by that? Well, I think it was Joseph Priestley. Please correct me if you know better. Maybe you've had a chemistry course more recently than I have. But I think it was Joseph Priestley who took like a log or a piece of paper or something and weighed it to as high a precision as he could, and then put it in a closed container and burnt it, and then captured, since it's in a closed container, captured everything that was in there, weighed all the ash and all that stuff. And it turns out the sum of the masses of all the ash and stuff ended up being exactly equal to the mass of the original log. Well, if you did that same experiment now, and you had the technology, say, to go to an infinite number of decimal places, or at least say, I don't know, 16 decimal places or something god awful like that, if you could actually do that, you would find that those two masses are exactly not equal. And in fact, their difference between the burnt and the unburnt is actually how much energy was put out by the fire divided by c squared. So this equation actually applies to everything. It doesn't just apply to, you know, nuclei when they combine and take 2 protons and 2 neutrons, the sum of the weights of which is larger than the 2 protons and 2 neutrons put together as an alpha particle. It applies every time there's energy created or converted in some way. So that's a big deal. Plus, it turns out kinetic energy, it's not 1/2 mv squared. That actually has to be replaced with kinetic energy equal to gamma minus 1 times mc squared. Okay. So these are all some of the equations you'll be needing to do your homeworks for chapter 36. But right now, I want to start off by looking at the addition of velocities formula that, again, I've showed you before. In Galilean relativity, we had velocity of A as seen by C. I told you all you had to do to make this equation a right transformation is you write V and you take that first subscript and put it here and leave a blank for the second one. then you say plus, and then you put V, and you leave that first subscript a blank, and then you put C, the second one. Once you have that, now you got to do is make sure this subscript and this subscript are the same. So if I put a B here, that would require a B there, right? Well, that's the Galilean formula, but the only difference is what I'm going to show you now by writing in red. The only difference is now in relativity, we have to add a 1 plus VAB, VBC over C squared. Okay, but we also need to remember the rule that Vij is equal to the negative Vj. Ooh, I wrote it backwards again. In real time, it's hard to remember that you're dyslexic and J's do not point the same way as I's. So Ji. Okay, so you got to have that caveat in there. So let's now, instead of jumping to using all these, because I've used a lot of this stuff before, I haven't used this, or this, but I think you can see it's fairly trivial to. What I want to do is apply this beast. And in fact, if you have, this is just when the velocity is along that one axis. Your book gives you some formulas for when it's along other axes, but I like this notation better. So anyways, I'm gonna give you this. So let's consider a problem. Let's imagine we got Earth right here. So this is example 1. And what we have is a spacecraft moving, and it's going to be called spacecraft A, moving at a velocity A with respect to Earth equal to, let's say, 3/4 of the speed of light. And then there's another spacecraft coming towards it, call that B. And in fact, that's moving this way so that the velocity of B with respect to the Earth, notice everybody has to agree which way is the positive direction. So in this case, this was going to be negative, and I'm going to do 7/8 C. Okay. So what I'm going to ask you is, what is the velocity of B as seen by A? Okay, this is all one-dimensional stuff. That's why I've dropped the vector symbols, because everything's going along in the positive or negative X direction. But for starters, we know that V is moving to the left. So A needs to agree that it's going to come out to be negative. And if this doesn't come out to be negative, we know we made a major mistake. So now I'm going to form my equation like this. And here's how I'm going to do it. So here's a solution. So the solution is velocity of A, or excuse me, of B as seen by A is equal to the velocity of B as seen by the Earth plus the velocity of the Earth as seen by A over 1 plus VBE BEA over C squared. But of course, we don't have VEA, so we're going to have to replace that with negative VAE. And the same thing here, negative VAE. So VBA is going to be equal to VBE, which is negative 7/8 C, plus VA, the negative of VAE. Well, the negative of VAE is negative 3/4 C. And all that's going to be divided by 1 plus negative 7/8 C times negative 3/4 C over C squared. So working it out over here to try to save some paper to some extent, VBA is going to be, notice there's a negative there. I can make this 3/4 into 6/8. So it's negative 7/8 plus negative 6/8 would be negative 13/8 C in the numerator. Now in the denominator, I'm going to get 1 plus, notice the C's cancel out with the C squared, and I'm going to get 7 times 3, which is 21, and 8 times 4, which is 32. So I have to make this 1 into 32 32seconds, which means I'll add 32 and 21, and that'll be over top of 32. So I now say it's negative 13/8 times C, which by the way is clearly bigger than the speed of light because that's an improper fraction. But when you add these two, I get 53/32. So this is equivalent to negative 13/8 times, now I'll flip this over, it'd be 32 over 53. Obviously, this is 4 times 8, and this is 8 times 1. So that 8 cancels out with that 8, and also there's a factor of C. So I now have 4 times 13, which is 52, and 8 times 53 just became 1 times 53. So that's 52 53rds negative C. That's the right answer. Okay, see, it got really, really close to the speed of light, but you know, Galilean relativity would have had us say that's actually going to be what, 1 5/8 the speed of light. 13/8 is 1 5/8. So no, this doesn't exceed the speed of light. Well, let's try another one. I'll call this example 2. Any questions on that before we go on? Everybody hopefully saw all the arithmetic I did. So example 2, if spacecraft A fired a photon torpedo. Photon is code word for the particle that is light, that makes up light, and therefore travels at the speed of light. That's the key thing to know there. So if a proton, or if a spacecraft A, that one up here, if that guy fires a photon at B, what will spacecraft B measure as the photon's velocity? Whoa, Nelly. I'll say speed. V photon with respect to B is question mark. And what is V photon with respect to Earth? Okay, so there's our questions. So let's first take off with part 1, or part A. So I'll label that A, and I'll label this B. Okay, so solution A, I want to know the velocity of P with respect to B. Well, that's equal to the velocity of P plus the velocity of something with respect to B, but I want it with respect to B. So what I need to do is find out what I have the velocity of something with respect to B. Well, if I look back up at the last problem, I had the velocity of B with respect to A. So I could do the velocity of A and A there. As long as they match, that's fine. Of course, I don't have VAB, but I do know that VBA is the negative of VAB. So I can just replace that with a negative. And then I'll go 1 plus VPA VAB over C squared. So that's going to come, the velocity of photon as seen by A. So now what I'm doing is I've added this photon here. And the velocity of the photon as seen by A is just the speed of light, right? If I'm the one that shot it, I should definitely see the photon leaving me at the speed of light. So I'm going to write C plus the opposite of VAB is VBA. So I got to take the negative of that. So it's negative 52 53rds. So I'm going to make this positive 52 53rds C. Now I'm going to divide this by 1 plus C times positive 52 over 53 C over C squared. Can y'all read those numbers? I know I'm writing very small. Now these C squareds definitely do cancel out. Here and here cancels out with there and there. So I get 1 plus 52 over 53. And lo and behold, if I factor out a c from here, I get 1 plus 52 over 53. So in fact, we get an answer that is just plain c. But that's supposed to be the case, right? Einstein's theory of general relativity said the speed of light is a constant independent of the motion of the source or the motion of the observer. So we just confirmed that with this crazy formula. Isn't it cool how it all just works out? Now let's try the second part, which is B, and I want to know the velocity of the photon as seen by Earth. Well, that's supposed to be the velocity of the photon as seen by something plus the velocity of something as seen by Earth. I'm going to use A again, and then I'll have 1 plus VPA VAE over C squared. The velocity of P as seen by A we know is C. The velocity of A as seen by E we know was 3/4 C. So I now have, again, notice if you factor out that C, you get 1 plus 3/4. Well, look what happens on the bottom. I got 1 plus C times 3/4 C over C squared. Again, you can see that this C and this, excuse me, not this C, duh. You can see that this C and this C cancels out that. So I end up getting 1 plus 3/4 in the bottom, 1 plus 3/4 in the top. And lo and behold, I get the answer is again C. Isn't that amazing? It's like Einstein knew some stuff. Any questions on those? So that's probably a good spot where you can actually see everything that we did for both of those examples. Any questions on that? So that's how actual velocities add. Again, your book gives you a formula for u sub x. It also gives you a formula for u sub y and a formula for u sub z, excuse me. And what they're doing there is they're, instead of using the symbol v for how fast the reference frame is moving, like I did here, they used the symbol u for how fast the frame was moving. And basically what they assumed was that the velocity, although it's the velocity has an x component, the velocity can also have a y component and a z component. And then they calculated how that would change, even though your particle's not necessarily moving with respect to the y or z axis, but just with respect to the x. So you can look at that in the equations. I usually do not do anything with that test-wise, but I might do something with that on the homework. So just be prepared to use those formulas from your book, but don't worry about doing it on an actual test, because that's a little bit more of the complicated stuff that you really don't need to do. But you can also see how they derive it, and that's kind of nice to work with. So let's see something about a momentum. Let's see what momentum is for an electron at a couple different speeds. So this will be our example 3. Again, nobody has any questions about this? We're quiet today. I hope that's not a bad sign. Okay. So this will be example 3. What is the relativistic momentum and the classical momentum when an electron travels at A, V equals, let's say, 2 times 10 to the 7th meters per second, and B at V equals, let's say, let's call this one 98% of the speed of light, 0.98 C. And let's go ahead and call this 2.0 so we can at least get 2 sig figs. Okay. Put a question mark there. Now let's go about working this problem. Does everybody understand the question? So part A, P relativistic is just going to be gamma times M times V, okay, which is mass of the electron, which would be 9.109. Almost wrote down the charge instead. It's 9.109 times 10 to the negative 31st kilograms times V, which would be 2.0 times 10 to the 7th meters per second, which you might recognize is about 1/10 of 2/3 of the speed of light. So about 0.0666 times the speed of light. Now I'm going to divide this by the part of the gamma that's in the denominator, which is the square root of 1 minus 2.0 times 10 to the 7th meters per second over 3.00 times 10 to the 8th meters per second. And all that quantity has to be squared. And what I can get is, I'll go ahead and calculate the gamma and just put that in front of MV, but then I'll actually give you the number right after it because I want you to see how far off it is from the regular MV. So I'm going to say gamma is 1 divided by the square root of 1 minus 2 e to the 7. Oh, I better put that part in parentheses. 2 e to the 7 divided by 3 e to the 8. Now I'm going to square that little part that's in the parentheses. So I'm doing 1 minus, notice you can see on my calculator, I'm doing 1 divided by the square root of 1 minus parentheses 2 10 to the 7th divided by 3 times 10 to the 8th squared. And that gives me 1.00223 MV. Okay, so literally we're like, if I move the decimal 2 places, we're 0.2% off by using MV instead of gamma MV. So now let me go ahead and multiply that by the mass times velocity. So I'll say times 9.109 e to the negative 31 times 2 e to the 7. And in fact, I get 18.25, or let's call it 18.3 times 10 to the negative 24th. And this should be kilograms meters per second. Okay. So now let's calculate the regular momentum. P classical is just MV, which I think you can already tell that that's going to be just the M times V. So I can steal that on my calculator and say enter, and I'm going to go back and erase the gamma part. So basically all I'm multiplying now is 9.109 times 10 to the negative 31st times 2 times 10 to the negative 7, I mean 10 to the 7th, and I get 18.21. Actually, I'll just call it 18.2 since I did that with 3 sig figs as well. 18.2 times 10 to the negative 24th kilograms meters per second. Okay, so you can see there's not a huge difference. In fact, the percent difference is really 0.1 divided by the correct one, which is 18.3 e to the 24th. and I get 0.0005, which is 0.5%. So really, when you're dealing with that large of a speed, which is a large speed, like I said, it's about 0.06% of the speed of light, about 0.06 times the speed of light, which is about 6% of the speed of light. We see that it's only less than 0.5% difference in using the relativistic versus classical value. Now, when we look at part B, we want to figure out what is the relativistic one for this velocity. So now we're going to say P relativistic is equal to 9.109 times 10 to the negative 31st kilograms times, in this case, the velocity is going to be 96% of the speed of light. So I have to put 98%, 0.98 times 3.00 times 10 to the 8th meters per second. And then all of that's going to be divided by the square root of 1 minus 0.98 C over C squared. Notice how much more efficiently it is to just write that as 0.98 C here, because the C is going to cancel out and life is golden. So just like I did before, I'm going to write this as some number times MV, and then I'll write it as a number all by itself. So I'm going to take hold on, my calculator's having a brain fart. Okay, so I'm going to take the gamma factor, and the gamma factor, you could actually pull this up from your spreadsheet that I suggested you make if you really wanted to. I'm going to say 1 divided by square root 1 minus, now I'm just going to say 0.98. I don't have to put parentheses around it because it's the only thing that's going to happen in there. So now I've done 1 divided by the square root of 0.98 squared. And that gives me 5.03 MV. Notice that's 5 times larger than the classical momentum. So I'll say this times 9.109 e to the negative 31 times 0.98 times 3 exponent 8. And you can see what I wrote down there. Again, I did 5.025, which was the number it gave me last time, times 9.109 times 10 to the negative 31st times 0.98 times the speed of light. And this gives me 1.35 times 10 to the, in this case, negative 21 kilograms meters per second. Okay, so you can see it's obviously a lot bigger, right? Now I'm going to just calculate MV. So P classical, which is just MV, is going to be essentially 267 times 10 to the negative 24th kilograms meters per second. Okay, so notice that did go up by like a factor of 100 compared to the classical one, because the classical actually by a factor of 10 roughly, because classically is 18.2 times 10 to the negative 24th, and classically again it's now 267. So that's almost, actually it's more than a factor of 10 larger. Of course, the velocity went up by about a factor of 10, so you sort of expected that. But that's it. Any questions on that one? So in general, what is the rule? When do you have to use classical versus relativistic? Well, generally they say whenever your energy's comparable to the rest energy, and that's the MC squared value, then you're right. So that brings me into introducing another type of energy called the electron volt. Okay, kinetic energy. Let's calculate the kinetic energies for these. So this is going to be example 4. What are the kinetic energies of the electron in example 3? Okay, so that's our next example. Let's calculate kinetic energies. Well, part A, the relativistic kinetic energy, Kr, is equal to gamma minus 1 times mc squared. Well, gamma, we can actually calculate. I'm going to go ahead and calculate gamma in both cases. We already found out, for instance, that gamma here is 1.022. So I'm going to say 1.00223 minus 1 times mc squared. So you see this whole quantity right here is actually just 0.0. Because when you subtract 1 from it, you get rid of that. So you can see this is about 0.2% of the rest energy. So this is an equation where you wouldn't want to necessarily worry about computing what the relativistic kinetic energy is. You just go with mv 1/2 mv squared. Now let's go ahead and do that calculation though anyways, just so we can see what it will actually be. And so that I can also add another unit to your quiver, if you will, to make sure you can work this stuff out. So I'm going to say this is 0.00223 times 9.109 times 10 to the negative 31 times 3.00 times 10 to the 8th meters per second. And that's going to be squared. So let's get what that is. I'm going to say again, 0.00223 times, now I'm going to write out the actual value of mc squared here, 9.109 e to the negative 31st times 3.0 e to the 8th squared, and I get 81.98 times 10 to the negative 15th. And this would be joules. Okay, so now I can actually put that as a number. So I'll say times times 0.00223, and that gives me 182. I should call that 183 actually. Proper rounding, 183 times 10 to the negative 18th joules. So that's how much kinetic energy it has relativistically. When I calculate it classically, K classical would be 1/2 9.109 times 10 to the negative 31st times 2.0 times 10 to the 7th meters per second quantity squared. So I'm going to say 0.5 times 9.109 e to the negative 31 times 2 e to the 7th, square that, and I get 182. Let me just make sure that's the proper rounding. Yes, this one does round to 182 times 10 to the negative 18th joules. Okay, so you can see it's only a difference of 1 at the 10 to the negative 18th place. Okay, but that also brings us to something. These numbers are ugly. I don't like writing exponents that much, right? So it turns out there's this neat little formula from electricity and magnetism portion of this course that says that basically potential energy U is equal to Q times the voltage. Well, normally that potential energy, like you've learned before, comes in joules. So what we could do is say that if I took 1.602 times 10 to the negative 18, or excuse me, 1.602 times 10 to the negative 19th coulombs, and multiplied that by 1 volt, then that would give me 1.602 times 10 to the negative 18th. Coulomb times a volt turns out to be a joule. And in fact, this is defined to be 1 electron volt. Notice how it looks like the symbol for the charge of the electron times the symbol for the voltage. That's a unit of energy, and it's that many. Notice that's 10 to the negative 18th. Wow, that's handy, right? So now I can say this one, if I just divide it by 1.602 times 10 to the negative 19th. Why did I say 19 there? It's supposed to be 18 there. It's supposed to be 19. Sorry about that. So now I'm going to do that first number, the 183. I'm going to divide that by 1.602 e to the negative 19. And that's going to give me 1.14 electron volts. Now I'm going to do the same thing with this one. I'm going to say divided by 1.602 times 10 to the negative 19th. And that's going to give me 1.1. This actually rounds to 4 as well. It's 1.137. So this one would have been 1.141. And I'm saying basically both of these last two digits are not significant because I only put in 2 with the velocity. So you can see that's a much better unit of energy to use. And in fact, the rest energy of the electron, this part right here, if I choose to convert that to electron volts, we will actually get a value that's pretty useful. So I'm going to say 9.109 times, or excuse me, e to the negative 19th, negative 31st, excuse me. So that's the mass, times 3 e to the 8th squared. That gives me, well, that doesn't look right. That is the mass of the electron. 9.109 e to the negative 31st times 3 e to the 8th squared. That is not what I expected to get. I'm not sure what's going on here. Let me check my constants real quick before I write down what I got there. I'm actually getting an 81 point something, but I thought it should be more like 0.5 times 10 to the 3 or something. Let me see. The mass of the electron is 9.109 times 10 to the negative 31st. Yeah, and that should be way different. Yeah, this actually turns out to be 0.511 MeV, where you have to convert it to mega electron volts. I don't know what just happened. But it keeps giving me something entirely different on here. And now I'm all concerned about these other values. So make sure you do these calculations yourself. I don't know what's going on. Might have made a mistake somewhere, but I know this for a fact happens to be the rest energy of an electron. It's supposed to be mc squared for an electron. That's supposed to be the mass of the electron, 9.109 times 10 to the negative 31st kilograms. This number, I doubt it's because I rounded up to 3, but it might be. But right now, that my calculator is calculating 81.98 times 10 to the negative 15, and that's just wrong. I just don't see why. So anyways, we'll leave that part at that. Let's go ahead and do part B now. So for part B, we're doing the same thing, but this time it's for 98% of the speed of light. So part B, I'm going to say K relativistic is actually equal to, remember we actually calculated the gamma factor before relativistically. We in fact found it to be 5.03. So I'm going to say 5.03 minus 1 times mc squared for the kinetic energy. So that's actually equal to 4.03 mc squared, which I'm going to say is 4. Actually, I'll go ahead and find the original value I had, because it was 5 point something other. I'm going to find that in my calculator. 5.025 to 5189 was gamma. So I actually wrote that up here just so you know that that 5.03 around it was that. So I'm going to take that number, enter it, and I'm going to multiply that by 0.511 MeV per C squared. So in this case, I get 2.57 MeV for the kinetic energy. Okay. Notice that is comparable to half a MeV, which is what the rest mass of the electron is. Now, classically, that would be 1/2 times 9.109 times 10 to the negative 31st kilograms times 98% of the speed of light would be 0.98 times 3.00 times 10 to the 8th. And all this would have to be squared. So I'd write squared and squared like that. So now I'm going to do 0.5 times 9.109 e to the negative 31 times 0.98 squared times 3 exponent 8 squared. So you can see what I put in my calculator. 0.5 times 9.109 times 10 to the negative 31st times 0.98 squared times 3 times 10 to the 8 squared. And that gives me 39.37, carrying 2 extra sig figs, times 10 to the 15th. Of course, this is still in kilograms meters per second, but we could convert it back to MeV. So I could also say, instead of that, basically 9 times mc squared, 9 is the m, and then the c squared. So if I just did 0.5 times 0.98 squared, I get 0.5 times 0.98 squared. Then that's the same thing as what I just did, times 0.511 MeV. So I can also write it that way. So 0.511 times 0.5 times 0.98, and I get 250, or 0.250, excuse me, 0 mega electron volts. So you see that's less than half of what the rest mass of the electron is. The rest mass energy, the mc squared for an electron is 0.511 MeV. This is 0.250, and you saw that it made up only a difference of 0.5%. So any questions on that? Now, there's other things you can use this for. For instance, you can take and look in the back of your book, and it'll have masses of various isotopes of atoms. So let me turn on my document, my regular cam now, since we've seen all this cool math problems type stuff. So for instance, if you wish, you can actually do nuclear physics calculations, which are useful. For instance, if you make a particle by combining 2 other nuclear particles, say for instance a proton, added to any nucleus, if you find that the mass of that proton, once it's added to the nucleus, whatever it becomes, if that mass is less than the sum of the 2 masses before, then that means it's going to give off energy, and it's actually bound, and it's going to naturally happen. If you have to increase energy, if you have to put energy in, that means it's not going to naturally happen unless you heat it up. In other words, if you've ever heard of the phrase cold fusion is a scenario where you can get two nuclei to fuse, that means come together, but have it at a normal low temperature. So when they say cold fusion, they're meaning maybe we can have this at 100 degrees Celsius or something, because right now it appears we need it at around 10 million Kelvin. So for instance, you can't fuse 4 protons into into a hydrogen, into a helium nucleus. You can't forge that unless you have an energy, ambient energy, if you will, of 10 million Kelvin. So the temperature would be 10 million Kelvin. That means the average velocity of those particles is large enough that they can overcome the repulsion barrier, the electric barrier that prevents a proton from running into a proton because they're like charges. But it's got so much speed at 10 million Kelvin that they will actually run into each other. And oddly enough, one might spontaneously become a proton or become a neutron, and the other one will stay a proton. So then you have a 1 proton, 1 neutron nucleus, which is still hydrogen, but it's called deuterium. Okay. If you had 2 neutrons and 1 proton, then it'd still be hydrogen, but in that case, it'd be called tritium. But in this case, you have that. And then if one of those particles were to run into another particle just like it, in other words, another deuterium, then those 2 deuterium will actually form a helium nucleus, which is 2 protons and 2 neutrons. That's the stable form of it. And it turns out that the mass of that is less than the mass of the 4 protons that went in. So it actually occurs appropriately, but it can only do so as a result of that first 10 million Kelvin. So the way you go about doing that, as you can see, for instance, in example, your book used, let's see, example 3611 and 3612 is something totally different, but it's useful for doing. But basically it says in example 3611, the energy required are released in nuclear reactions and decays comes from a change in mass between the initial and final particles. In one type of radiation decay, an atom of uranium, which has a mass of 232.03714 unified mass units, okay, decays to an atom of thorium, whose mass is 228.02873 unified mass units, plus an atom of helium, 4.00260 unified mass units, where the masses are given in those atomic mass or unified mass units, and they give you a conversion. What they want you to do is calculate the energy released. Well, all those tables all those masses was masses that came from the table of isotopes in the back of your book. So if you look in the back of your book in the appendices, I'm gonna try to find it real quick. Hold on. So starting appendix page 49, I think, no, 48 appendix page is where the index starts. Then the answers to the odds are, of course, on the pages before that, all the way back to appendix, I'm thinking maybe 25 or so. Nope, it's even less than that. So yeah, those actually start at appendix, the solutions, the answers, that is, starts at appendix A18. But at A14, A14, 15, and 16, that's the actual masses of selected isotopes, which you may or may not be able to see because the glare on my screen right now on the page. So you see all those. And I don't want to show you them in detail anyways, because this is copyrighted material, but you can see the tables there. But what I want you to understand is that when you look on here, you'll see atomic mass, and I'll have a little dagger by it. And you look down, whenever you have a little dagger like that by, that means there's a footnote down. So I look down at the footnote, it says the mass given in column 5 are those for the neutral atom, including Z electrons. So that's the main part I wanted to clarify with you. But notice if you take uranium 237 and thorium, whatever one that was, you're counting up the electrons in uranium 237, and you're counting up the electrons in the thorium. And then you're comparing it with the electrons in the alpha particle, which is the hydrogen or helium. So if you look at that, it turns out that you're sort of canceling out the same number of electron masses. So that's all good. That's why you can actually use that table. So table A14 or appendix page A14 is where the selected isotopes are. And that's where you can find those values like the book actually gave you in that example, which I told you was 39 or 36-41 or something. So any questions on that? Yeah, it was example 3611 was that one I was talking about. I don't cover the Doppler shift, but you can see the formula is quite simple. And when you compare it to what we do in sound, you can see it's quite different from that. But I think I did put some Doppler shift equations on there, but you can see it tells you equations 3614, which has 14a and 14b, and then it has 3615, which is 3615a and 15b. But they tell you what's going on in each of those courses, in each of those equations, so you can know which one to use. So for instance, 3615a is when the source and observer are moving away from each other. And so is the equation 3615b. But when the source and observer are moving towards each other, then you have to use 3614a for the wavelength or 3614b for the frequency. So I'm just giving you that just so you can do the couple of problems that might appear in your homework. I will not be asking you those type questions in the actual test, but still I think it's good that you have some practice with it. So all I really have left to cover is what the total energy is, and that comes in pretty handy as well. So let me give you one more neat equation. And that neat equation is the total energy of anything. Okay, so relativistically, the total energy, so I'm going to kill this right here. It turns out that, and your book explains why this is the case, and you know, can even, in some sense, you can go through a derivation, or you can read Einstein's words on this. But basically, it turns out that E squared, the total energy that anything has, is equal to the momentum squared times c squared plus m squared times c to the fourth. So what you're seeing is any particular particle has an energy E given by its momentum and its rest energy. In the case of a photon has no mass, so this disappears and you just get E is equal to PC. Okay, but in everything else that's not massless, you have this term over there. So this sometimes can be used, but you can also remember that in conjunction, you know, the kinetic energy is equal to gamma minus 1 times mc squared. So all of that combined, you can say, oh, if this is gamma minus 1 times mc squared, that's probably represented in this, because this is the energy related to its momentum, which is mass times velocity, right? It's gamma mv specifically, but then it's times c squared. So you can see evidently this and this are sort of the same. But anyways, I wanted to make sure you'd seen this equation. Our time's almost up. And there's that kinetic energy equation. So does anybody have any questions on this? I think I might be able to fit in one more example. So let's take the, let's consider one TeV electron. That's one teva electron volt. Okay, so that's a big unit. Teva is 10 to the 12th, for instance. Whoa. Okay, there's a problem. That's okay. I think I have another pad right here. Whoa. Yes, I do. So this would be example 5. So one of the reasons I want to show you this is there's some common wording that confuses students. But when someone says, what is if someone says, what is the speed of a certain energy particle? So let's say, what is the speed of a 1 TeV let's say photon, no, let's say proton. And then part B, what is the speed of a 1 TeV electron. So when they say that, they tell you an energy, that means kinetic energy. That's the main reason I wanted to make sure I work this example with you. This is the kinetic energy, okay? So what we're going to do is we're going to work this out. We're going to say, okay, 1 TeV is equal to 1 times 10 to the 12th electron volts. Okay. And of course, we could convert this to joules. I'm going to do that right now just for the heck of it. We know that, for instance, 1.602 times 10 to the negative 19th joules is equal to 1 electron volt. So that electron volt will cancel out if I just multiply it by 1 times 10, 1.602 times 10 to the negative 19th. So I'll say 1 e to the 1/2 times 1.602 e to the negative 19, and I'll get 160.2 times 10 to the negative 9th joules. So it's still a small amount of energy on a macroscopic scale, but it certainly is a lot bigger than the stuff we're normally used to working with. So now I have that, but I also know that the kinetic energy is gamma minus 1 times mc squared. So I can say that 1.602 times 10 to the negative 9 joules is equal to gamma minus 1 times mc squared. At this point, you can see, oh crap, Mr. Younger converted everything to joules, but I happen to know mc squared for the electron, so I could have put the 0.511 MeV in here, and then I could have got it without doing all this, but that's okay. We can still do it this way as well. So now what I'm going to do is solve for gamma. And what I'll do is I'll say kinetic energy is equal to gamma minus 1 times mc squared, which means gamma minus 1 is equal to k over mc squared, which means gamma is equal to k over mc squared plus 1. Okay. And of course, we know gamma is equal to 1 over the square root of 1 minus v over c, quantity squared. So if I take gamma squared, then I get 1 over 1 minus v over c squared, which is, we could just solve for just beta, and that would be a pretty good way of doing it. So now what I'll do is I'll say 1 minus beta squared is equal to 1 over gamma squared. Now I can see that beta is actually going to be equal to the square root of gamma squared minus 1 over gamma, and that's probably the best way I can do it. So now all I have to do is plug all that junk, what this is equal to, in there. Now, obviously, that's not necessarily going to be pretty, but I can do it. So I'm going to say gamma is equal to k, which is 1 times 10 to the 12th. Actually, let's go ahead and use the value I calculated since I already did it in joules. Let's do 1.602 times 10 to the negative 19th joules divided by, now we're talking about the proton here in part A. So the proton has a mass of let me double check. I think it's 6.607 times 10 to the 28, 10 to the negative 28. Oh, glad I checked that, 1.67. So many constants in my head. 1.67 times 10 to the negative 28, which notice is about a factor of 1,000, larger than the electrons, times 10 to the negative 27. I said 28, but I meant 27 kilograms, times 3 times 10 to the 8th meters per second, quantity squared. And then, of course, I've got to add 1 to it. So with that in mind, I'm going to say this big value right here, the 1.602, ooh, that was 160.2 times it. Ooh, everybody notice this. I made a copying error from my calculator. See that result? 160.2 times 10 to the negative 9. I didn't even notice where the decimal place was. So this should actually be 160.2 160.2 times 10 to the negative 9. That means this is going to be the same thing. So 160.2 times 10 to the negative 9. So I'm going to say that number, and I'm going to divide it by parentheses 1.67 e to the negative 27 times 3 e to the 8th, and I'm going to square that. And that's going to give me 1.066 times 10 to the 3 minus 1. Now notice we're talking about 1,000 minus 1. Does that really matter? No. So I'm going to say that's approximately 1.066 times 10 to the 3 is the gamma. Okay. Now, actually, it's 1065 if you really wanted it, because I did actually write that many sig figs, but technically I never had that many sig figs to begin with, so I really shouldn't be doing that. But there it is. It's a unitless quantity because it's kinetic energy over energy. So now that means beta is equal to 1066 squared minus 1 square root of all that divided by 1066. And that'll give me the fraction of the speed of light that it is. So I'm going to say that 1.066 that I had, I'm going to square that, and then I'm going to subtract 1 from it, and then I'm going to take the square root of that, and then I'm going to divide it by the same thing. And lo and behold, I'm going to get basically 0.9999996. So it's basically 99.99996% of the speed of light. So that's what the velocity is. Very, very fast. Now, if we did the same thing for the proton, for the electron, that's part B, we're going to get even larger value. So you can see, again, 1 TeV, that's still going to be, in this case, let's actually keep it as a TeV. That's 1 times 10 to the 12th EV. I'm going to keep it in EVs and realize that's equal to gamma minus 1 times MC squared. But for an electron, MC squared is 0.511 MeV. So I'm going to say 1 times 10 to the 12th EV is equal to gamma minus 1 times 0.511 times 10 to the 6th EV. Remember, mega electron volts is 10 to the 6th. So you can automatically divide out 10 to the 6 on both of these and just get a 10 to the 6 here. So I now got 1 times 10 to the 6 is equal to gamma minus 1 times 0.511, which means gamma minus 1 is equal to 1 e to the 6 divided by 0.511. So we're essentially multiplying it by 2, and I get 1.95995, let's say 9569. That's what that is. And that means, of course, gamma is equal to this plus 1. So gamma is equal to 1 plus that answer. Oh, that was times 10 to the 6, by the way. Okay. So again, eventually I just get, of course, gamma is approximately 1.9569 times 10 to the 6th is really what gamma is. So now I can say beta is equal to 1.9569 times 10 to the 6th squared minus 1 over 1.9569 times 10 to the 6th. And that should give me my beta for the actual electron. So now I'm going to take the square root of this 1.9569 times 10 to the 6 squared. I'll subtract 1 from that. And now I'm going to divide it by 1.9569. And this gives me 1.0, even when my calculator carries it out to 12 decimal places. Notice it gave me 1.0. So usually when I do this, if I multiply it by something else, it'll give me all its decimal places. So watch this. Let's say multiply by 3. You can see it went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12 nines followed by 8, 5. So it's 0 0.123, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think that's how many it had. 8, 5 C is what the velocity of the electron would be. So that's really a huge deal. Obviously, an electron at 1 TeV is going super, super fast. 1, 2, 3. I'm counting my digits to make sure. 4, 5, 6, 7, 8, 9, 10, 11, 12. Yep, it was 12 exactly. So that's it. We finished relativity in its entirety. So you should be able to finish the homeworks tonight. Today's Wednesday, right? Yeah, tonight the conceptual questions are due, if I remember correctly, and Sunday the first set of mathematical problems is due, and then Wednesday the next set of mathematical problems for chapter 36. There's 2 sets for this chapter. So again, you've got everything you need. Time is up. You're free to go, but don't forget the equation sheets now on Canvas, and stick around if you have any questions. I'll wait for the last person to leave.
Have a good night.
You too.
Thank you.
You're welcome. Thank you.